Hello friends, you are welcome to my series Embedded Design in Electrical Power Domain. And today we are entering the part 8. What we have done so far, let us briefly have a look at the activity area of embedded design. We have seen has three parts in it: monitor, control and protect. I had also mentioned that without monitor you can neither control nor you can protect. So we took monitor at a length and saw various things that need to be monitored: the current, the voltage, frequency, power factor, and so on. And we have seen the examples also. Then we went to control. Here we have seen this, and now we are entering the protect area. Protection functions in electrical power systems. That is what we are going to take up today. Now we need to protect electrical power systems against a variety of threats. And the way you do it is you make a protective relay. So such devices are called protective relays. So these relays are classified in terms of, number one, nature of threat, like overcurrent, overvoltage, under frequency, overfluxing. As you can see, that overcurrent would really mean that you are heating up the machine and therefore you are risking the life of the machine. Same thing happens with overvoltage. Overvoltage really affects the insulation. In fact, overcurrent also hurts insulation. Under frequency, overfluxing, etc., they are all threats to power system, and to protect the power system we must develop appropriate protective relays. Shown two examples here. This is a feeder protection relay. Is some kind of a self-powered relay. The other type is way of naming them is type of equipment to be protected. For example, you want to protect feeder, you want to protect generator, you want to protect motor, and so on. This is a huge list. Then there is a nature of its power supply. Now a self-powered relay or auxiliary power relay. So it can be either or it can be both. A circuit breaker relay is generally a self-powered relay, but many times they add an auxiliary supply also. The purpose of this auxiliary supply is to be able to monitor the contents of the relay, to be able to see the history of the relay, because while this relay is working, it stores a lot of parameters, lot of vectors in its non-volatile memory. So how to access it? If there is auxiliary supply, then only you can access it. It is there, but you cannot access, because once the relay trips a circuit breaker, current becomes zero, and when current becomes zero, the self-powered relay is as good as dead. It cannot respond to anything. And that's why if you want to access something from it, then you must connect to it an auxiliary supply, and then you can start communication. You can use the front keyboard, or you can use serial communication, whatever is available, like that. So that is the purpose of a auxiliary supply in the self-powered relay. So we will focus on the nature of threat. We will focus on this nature of threat, like overcurrent, overvoltage, and so on, because that is where embedded design concepts need to be realized. So if you can handle these things, then that is what you are expected to do. And one very important thing is, we are not following just any kind of relay characteristic or nature of threat. We are strictly following the international standard called IEC 60255 for definition of relay characteristics. So friends, let us move over to the next, current protection. We start with the current protection. This is perhaps the oldest need, and the most common also. We'll start with overcurrent and short circuit protection. Short circuit is the extreme case of overcurrent. So IC 60255, it provides a trip curve. This is based on IC 60255. So if you look at standard inverse, so what actually happens is if the current is something like 5 times, it goes from normal and becomes overcurrent and reaches something like 5 times, then we follow this characteristic. Higher the value of overcurrent, faster it trips. This, you can see, this is the time axis and this is I upon IS axis. So if it is 5, then you are somewhere here. If I upon IS is 5, then you are somewhere here. That is, after so much time, you will trip. If it is 3, then you take about 6 seconds to trip. If it is 2, then you take about 10 seconds to trip. So higher the severity, shorter is the tripping time. This is logically okay. So you can see here these parameters. This shows 0.1 in the inverse characteristic. This shows second point, which is still 0.03. This is the third one. It is 6.30. Then comes 5.52 when I upon IS is 4. Then this. So like that you can see that at 5 times the overcurrent value, you get this. So like this it goes on. Now this is the equation given by IEC 60255. Here TMS is time multiplier setting. You can see that T, that is tripping delay, this is called tripping delay. Here I have mentioned it as TD, this is the tripping delay. And this is equal to, TMS is equal to K upon I by IS raised to the power alpha minus 1. Here TMS I am taking as unity. Then K and alpha are defined by this standard. It is here. The curve type, and we are referring only to inverse characteristic, not to this, but only to this inverse characteristic. So this characteristic is also having 4 different forms. First one is standard inverse. Now K will change. K is 0.14 and alpha is 0.02. If you take very inverse, then K is 13.5 and alpha is 1. So K and alpha are defined in the IEC 60255. Then it can be extremely inverse, where K is 80, alpha is 2, or long time standard inverse. It is K is 120 and this is 1. And you can see here that this K is in the numerator. And so higher the value of K, higher is the tripping delay for a given I upon IS. So for a given I upon IS, you have higher the value of tripping delay, higher the value of K. This is the shortest. And then this is longer than that. It is 13.5, this is 80, it is 120. That is one thing to note. The second thing to note is, here the raised to the power, I upon IS raised to the power is 1. Here also it is 1. And here it is 0.02 and here it is 2. Why I am saying this? Because this involves doing mathematics in your relay program. And that's why we'll look at it separately again. But you have to make this, note it down in your mind that this and this, extremely inverse and standard inverse, require raised to the power alpha, because alpha is not 1. So it could be 0.02 or it could be 2. Now let's take example. Suppose I upon IS is 2. I upon IS is 2. Then what is the tripping delay? Substitute the values. TMS I am taking as 1. So K is 0.14 from this standard inverse. See here I have written standard inverse. So it is standard inverse. So K is 0.14 and alpha is 0.02, 2 raised to the power 0.02 and so on. If you do calculation in your calculator, you will find that is 10.03 seconds is the delay in tripping. So once this situation arises that current has suddenly become 2 times the rated current or set current, then it will take 10.03 seconds to cause tripping, to send tripping command to the tripping relay. Similarly, if I upon I becomes 3, then it will take almost 6 seconds, to be exact 6.30 seconds before it initiates a tripping command. So provided that I remains constant until tripping signal is issued. You see the importance of this statement? I said it is 2, then the time required is 10 point something. If it is 3, I upon I is 3, then you require so much time, 6 seconds approximately. But can current remain constant? That is, will I upon I remain 2 all the time? Once it becomes 2, it remains 2? No, it can change. And so how will you substitute values here? How will you substitute I upon Is? How will you decide what the value of t if this changes from 2 to 3 to 4 to 5 or back to 1? If it moves in and out like this, then how you are going to realize this equation? You cannot. You started this, say, at 2 seconds, as 2 times. So I upon I is 2. And so you calculate the time required is 10.03. But let us say after a few seconds, say 5 seconds, it changes to I upon I is equal to 3. Then all your calculation will go haywire. Therefore, this is rewritten in a different way. This is how we rewrite this equation. Here, the time delay, you have multiplied the lower part here to, and therefore this multiplied by t is on the left hand side. Tms is 1, so I am ignoring it. And then on the right hand side you only have k, nothing else but k. So look at this. So instead of ti, I have written delta t and I have put a sigma, because for some time the value of I upon I is something, later on it changes to something else, and therefore every time you can get update. So this thing which is in the denominator, to that I multiply by t, call it delta t sigma. And then on the right hand side you only have k, assuming TMS is 1. If TMS is not 1, then bring it down, and on the right hand side you will only have k. Okay, so this is how equation 1 is brought to life. Then we go over to the next. What is delta t here? Every time you insert I in the summation, this is the summation we are doing. Every time you insert the value of I, you must have an updated value if you are taking 20 samples per cycle, and if you operate in a 50 Hz system, and if you are able to update RMS value of currents in every interrupt, then delta t is 1 millisecond. Okay? How? Cycle time period is 20 milliseconds. And suppose you are issuing 20 interrupts per cycle. It gives a sampling interval of 20 millisecond upon 20, which is equal to 1 millisecond, which means that interrupt is coming every millisecond. Now, with I upon I is equal to 2, we can write sigma 1 to n of 1 millisecond into this, the same thing, what is written here. And this is equal to 0.14. After how many n's, after how many summations will you have 0.14? That will decide how the tripping delay. Suppose it takes 100. If you do this summation 100 times, which means n equal to 100, and you get left hand side equal to right hand side, then it will mean that 100 into 1 millisecond, that is 0.1 second, is a tripping delay, right? Do you get it? So I repeat, if suppose during this summation you find that this left hand side becomes equal to right hand side after 100 operations. So 100 times you are reading IS 100 times, right? And the interval between two readings is 1 millisecond. So 100 into 1 millisecond is 0.1 second, after which you will issue tripping command. Since I upon IS is not changing, then we will go on accumulating this number until it equals RHS, which is this. So what do you do next? You have earlier obtained the value here, 10.03 and 6.30, and the same value you are getting here. So we find that is 0 you obtain here, and here I have put 1.014 minus this, and therefore it takes 10 seconds. So if I upon IS is 2, then it takes 10 seconds approximately. If I use this equation, which means whatever we have done is justified, purely justified. And then we go to the next one to verify another thing. That is, if I upon IS you get 3, in that case you substitute the values in the same equation and you will eventually say that the time delay is 1 millisecond into 6363, which means it takes 6360 times addition to get LHS equal to RHS. Left hand side is equal to right hand side. So these two results match with the results obtained by using this equation. This was the original equation and we converted it into this kind of equation. Done? So in both cases you get identical result. So we can safely use this equation. If these two results match with the results obtained by using the equation this, then why go for the tedious summation process? In this given example, the overcurrent factor is 2. If it stays there, then tripping signal will be generated after 10.03 seconds as shown in the graph. So 2, this we have seen using the standard equation. But if I upon IS becomes 3 after 5 seconds, then how will you decide the tripping delay? This is where equation 1 comes into picture, this equation 1, or modified tripping equation. So this equation does not bother how current is changing. It just measures the current and puts the value here and keeps doing the summation. And when left hand side equals right hand side, it issues trip command, as simple as that, right? So let us see, let's verify this also. When LHS equals or just exceeds RHS, then you issue tripping command, as simple as that. Now in this situation, in this equation, what is the sum on LHS after 5 seconds? So for 5 seconds, this ratio was 2. For 5 seconds, this ratio was 2, and then it did not trip because with this ratio of 2, you will take 10 seconds to trip. But now, after 5 seconds itself, it has moved over to 3. I upon R is equal to 3. So let us see how much heating had happened where we had moved into this equation. So we'll see that 3 raised to the power 0.02 minus 1 raised to the power n, multiplied by n plus this multiplied by 5 is equal to 0.14. Are you getting this? What we are doing is, we have seen that for 5 seconds it is 2. So with the help of I upon I is equal to 2 and time equal to 5 seconds, we calculate LHS, and that LHS value will be this, right? This is obtained from here, from this equation. So the LHS value up to 5 seconds is this, and we have to go up to 0.14. So how much time it will take for this to, so that's the sum of these two quantities is 0.14. So this becomes 0.022 raised to the power multiplied by n. We want to find out n. So n is equal to 3.19. So total tripping time is equal to 8.19 seconds. We do it in another way, that is, here initially I upon I is 3. Earlier we had taken 2. Now I say it is 3. It would have tripped after 6 seconds. But before that, that is after 4 seconds itself, you get the current reduces and falls to I upon I is equal to 2. Now when will you issue tripping command? Nothing, not to think much. You just substitute values. You keep getting these values. When you write a program, you are reading values from the interrupt, and you keep inserting those values here. Keep inserting one after the other, like that. And so when you process like that, you find that tripping will happen at 5.71. You have a careful look at all these things that I have mentioned. Now inverse characteristics are used only up to I upon I is equal to 5, or it may vary from relay to relay. So up to 5, almost up to 5 or 4 in some cases, you use inverse characteristic, and after that you use the definite time characteristic. And then a time comes when you say that no, it has to be done, it is so high current is so high that you must trip immediately, then you don't wait for time. Here current is very high, but still you are in a position, you are willing to do some waiting. You know, when this situation arises, when you switch on a motor, then the motor takes almost 6 to 8 times the current. And so if you don't provide sufficient delay, the relay will trip it directly. So you switch on a motor and the relay will trip it. Again you switch on the motor, relay will trip it. What is the use of having such a relay? So when the value is like this, something like 6 to 8 times the rated current, then you say, okay, perhaps it is starting, the motor is starting, the machine is starting. That's why it has taken such a high current. And so let the machine start. So you provide some time. In this case, you can see it is something a little more than 2 seconds. So motor will start within that time period. And moreover, this is adjustable. If you find that the motor is taking longer, then you can set the value to something higher, right? Give it more time. Otherwise, unnecessarily, you will be starting and tripping a motor and never start your real job. So friend, we have a definite time delay as well as instantaneous. When current is very high, it means it is not really starting current, it is something else. There is fault and therefore you must trip it. Then you trip it directly. So friends, this is where I conclude the overcurrent concepts, and we'll meet in the next episode. Thank you.